Everybody, welcome to the latest in our series of lunchtime seminars. Today we have Alan Taylor. Many of you know him, but I'll introduce him anyway. Alan Taylor graduated from Salford University in 1969 with a degree in civil engineering. After a period working on various engineering projects, in 1979 founded A.J.L. Taylor Limited to manufacture software-controlled pipe organ control systems. First system used 256 bytes of memory and is still working today over 45 years later, which I think is impressive for any kind of digital system. In addition to producing control systems, the company also developed a range of other organ-related products which are to be found in chapels, churches, cathedrals and concert halls throughout the world. Since retirement in 2006, Alan has concentrated on pipe organ wind systems and in 2019 completed a postgraduate research degree. Today's presentation focuses on this research with particular reference to reservoir resonance. So without further ado, I will hand over to Alan, who will tell us about reservoir resonance.
Thank you. Good afternoon, everyone. I thought I'd start off with this slide because this is quite a concrete, a new organ that's probably 20 years old now in Disney, Huntsville in America. And it doesn't look anything like a pipe organ at all. But it is a fully functioning pipe organ built by Reservoir and Reservoir in America. Things happened.
Try the down arrow.
Sorry?
Try the down arrow.
Oh. I thought I'd start off with a little organ meeting, then we all know what we're talking about. Briefly, we need to know where we come from so that you can understand what it's all about. So brief history on what an organ looks like. A bit about organ pipe flutter, that's what my research is based on. The influence of the blower or fan. We call them blowers in organ building, not fans. And then we got onto reservoir resonance. The shaking stop is the vibrator or tremulant, and then what next? In Salford, we had 3 pipe organs. We have none now. There was one in the Maxwell Hall there, and you can see the console and the 2 chambers on each side of the stage there contain the pipes. Swell and choir was over here, great and pedal was over here, and there's the console there. And it was used quite a lot in the 60s and 70s. And this is the installation of Prince Philip as Chancellor in 67. And there's the college organ. We had quite a strong music department in those days, and that's Herbert Winsbottom, who was head of music. The organ came from Peel Hall or Peel Building. This is the Alexander Young organ that was in, and that was transposed from there into Maxwell Hall. That was, I think it was 2 mile, and they extended it. And then in the 70s, early 70s, they got an idle church organ, and that lasted here for about, I think, 2000, and then they got rid of it. We had a third organ, which was in the building, the maintenance building, which was opposite Peel building, and that was a little practice organ. A small 2-rank extension organ built by Rushworth. So we had 3, and you've got none. Not even electronic nowadays. You've got to go to America to find the biggest pipe organ, which has got 33,000 pipes. The biggest working pipe organ is still in America, and that's in the Wanamaker store. This one's in, I think, Atlantic City. To put this into context, the organ in Liverpool Cathedral contains nearly 11,000 pipes. So that's organs 3 times the size of the one in Liverpool Cathedral, which is the largest we've got in the UK. We go back a long way for pipe organs, and this has got all the features that you would see in a modern organ. We've got a wind system down here. This is actually pressurized by water. So you've got 2 feeders here, or pumps, hand pumps. So you've got one person on this side, one person on the other, pumping it. So we've got a wind system. The other important thing is we've got a set of pipes, and we've got a mechanism, a keying system that allows you to operate the pipes. So we've got, this is the stop, which enables a complete row of pipes, and this is the key. So you can select individual pipes from that. Designed by a Greek engineer. So this has still got the same features, but it's looking more like an organ now. We've got the player here and the keys. We've got the pipes, and we've got the wind system here at the back. And there's 2 divisions on this organ. There's one division behind the player, positive, and there's one division here in front of them. And this here is casework, so the player wouldn't see the antics of Lord's getting, mine's blowing the organs getting to the back. And the action is quite simple. You've got a key here, through a kind of wooden tracker to this backfall, and then to the pallet here that opens the pallet. This is a more modern arrangement. We've no longer got the hand blower, but somewhere around here it would be a centrifugal blower, feeding these 2 reservoirs here, one there and one there. This reservoir is for the swell division, and this reservoir is for the grate and the pedal here. We've got a similar kind of arrangement. This is operating pneumatically. From the keys here to the pull downs here on the sandboard, it's done by wind. And there's still maintain on this a hand pulling crank just in case the electricity goes off. Or alternatively, you can use the electricity of the hand blower doesn't turn on. And you can see the arrangements of pipes. They're all different shapes and sizes. This gives you a better view of the pipes here. So we've got metal ones, wooden ones, some which are stoppered, some which are open. And to give you some idea, this is a pipe that sounds roughly 1K, which is my test pipe. So that's, and we measure pipes in feet. So that's a 6-inch pipe. This is a 3-inch pipe, which is 2K. And then we go down to a 4K pipe. No, this will really test me. This is 8K. So if you've got hearing aids, turn them off. Can you hear that?
Gosh, yeah.
So those are the top pipes, and imagine trying to tune those. I can just about hear that. And on the extreme, we go to these pipes, which are 32 foot long. And that's an open pipe. So it would give a frequency of about 60 hertz. And on the recording that we heard at the beginning of Bart to Carter, when he put the pedal note down, he was actually playing 32 foot open and pedal reed at the same time. So the bottom notes, well, it got 60, it was a D, not a C, so it was just above 16 hertz. If you actually block the end of the pipe up, then you'd actually get 8 hertz thereabouts. And the organ Paso in Germany's got a 7 hertz bottom pipe, which they use occasionally, and they warn people that don't use it. So you've gone from that to that. So we move on from the pipe sound and get on to what we really want to talk about, the wind system. This is a typical wind system that was originally hand operated. And then with the Industrial Revolution, we got water engines. So this was replaced. This is actually side elevation looking up there. This part of the drawing. So we got 2 water engines here operating these 2 feeders, 2 bellows. And they're supplying these reservoirs at the top, 2 single rise reservoirs. The next big development is the electric motor. So we have here a crank arrangement with 3 feeders, like a 3-cylinder Citroen car engine. So on the end of here, you've got an electric motor that's turning this crank round, and these things are going up and down. So it's keeping wind supplied into this set of double rise reservoirs. And if you notice, one set of ribs are inward folding and the other set are outward folding. And that's because they're self-compensating. So you can get changes in the height of the reservoir, and it doesn't affect the wind pressure. This is one of the first centrifugal blowers. So you can see it's basic cruciform arrangement made out of wood, bolted on the end of a 750 RPM motor, and it just spins around and hopefully get out of here. And this shows a typical modern blowing system now, where we've got a staged set of fans. So we start off here with low pressure, and the air goes in here, and it feeds each stage. So you end up at the end here with what's called high pressure, and you take the low pressure off there, and then this is action pressure here. And this is a little control system here that governs the speed of the motor. So this is connected to usually one of the, to this reservoir here. And as this goes up and down, it alters this rheostat here, rheostat, and alters the speed of the motor. The earlier hand blowing system was self-regulating, but now you've got a fan, you need a cut-off valve, just like a ball cock on a water storage tank. So you need a cut-off valve. So this is a simple arrangement connected to the top of the reservoir. The reservoir goes down, lifts the valve up, and this is what's called a roller line. That's the guillotine. This is a roller line. And it's the same thing on the reservoir comes down, the road line goes up. That's wind in, the reservoir goes up, and so it's self-compensating. This is a small little blower, fractional horsepower in a cabinet, that's acoustically lined, so it's pretty quiet. So this would stand just outside the organ, whereas this is a blowing plant that's probably makes a lot of noise and is in a basement or somewhere else, a blowing room. Organ builders are mainly concerned about quantity. You need enough quantity, otherwise the organ's silent. So it's important that you get an adequate supply of wind and you get it at the correct pressure, because pipes are very susceptible to pressure. If the pressure goes down a little bit, the tuning will change. So it's important that you maintain, it's a bit like gas. You know, you need the right gas pressure for your boiler to work efficiently. My research was more in looking at the quality. If you've ever tuned a pair of pipes, so you tune these, and you would listen to the beats, and you would tune them so there's no beats. But what I found, and what a lot of organ builders found, is that there is this flutter in the background from the wind. And that really does make it difficult when you're tuning and listening for beats at 2 and 3K pipes. It becomes difficult. So I was looking at, could we improve that quality of wind? And that's where the research started. So this is a traditional double rise reservoir that's fed by this piping here with 2 gate valves on. So you can blow it up, leave it, and it will, because it's got this self-compensating mechanism, doesn't matter if it goes down a little bit, it will feed the pipe at the same pitch and pressure. This here is a traditional single rise that's fed using a guillotine valve, and you can hear the difference between the two. That was pretty pure. This is the electric one. Can you hear the flutter on there? Now imagine trying to tune 2 pipes, especially high frequency pipes, with that going on in the background. And I'm looking at a man who once said to me, if you can hear it, you can measure it. And so I did. So I built this test rig here. That's it can be weighted or it can be sprung, and the measurements in the form of a microphone or an accelerometer. And we've got the basic features that we need. We've got a reservoir, a blower, and we've got a tremulant here, which forget for the moment. So the initial measurements produce this. So the green is the good wind, the hand blow, and the red is the electric wind. So you can see the difference. So we can actually prove that we are listening to impure wind. And this is based on the reservoir top, the vibrations at the top of the reservoir. If you look at what's happening on the pipe, again, green is for the hand and red is for the electric. You can see these 2 sidebands. So you've got this sideband modulation, which is the cause of this flutter. So I produced a MATLAB script to simulate it. So there's a drop-down menu here, go from 8K down to, I think, 32 hertz. You can change the modulation frequency from 2 to 20. And you can alter the percentage of modulation from 1% up to 9%. And then there's a multiplying factor here of 1. Sorry, 10. So you can actually scale it up. So if you listen to what 1% is, you can hardly tell there's any flutter there. Now, if we go to 2%, you're beginning to hear it now. Could you hear that? You perhaps need to move your head a little bit to kind of get in the range. And certainly if you go to 3%, you can hear that, you can definitely hear 3%. And we're getting similar sidebands that we saw on the measurements that we took. Resonance, that's what it's all about. And we all know about breaking glasses, wine glasses. And I thought this is a good example to show the catastrophic effects that you can get with resonance. You're all aware of this bridge, yes, and how it shook itself apart.
Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
This bridge was opened in July 1940. And that happened in November 1940. And when it was being constructed, they realized there was something wrong with it, and they actually had temporary anchor cables from the deck to stop it swaying around all over the place. And they commissioned a report to see how you could fix it. The report it came out on the 2nd of November, 5 days before it shook itself apart. It's 2,800 feet long, and the actual deck itself is only 8 feet deep. At that time, they would have normally used a lattice girder deck, which would have been 3 times the depth. And extensive wind tunnel testing afterwards, they realised the mistakes that they made. In fact, the recommendations were to add some kind of deflectors to the front edge of the beams to actually divert the wind from the actual beams themselves. This is my version of it to show resonance occurring in reservoirs. This is a fairly modern vertical reservoir here, so it's got very little mass. There's an electric motor, DC motor here with an out of balance 6mm screwed rod. It's only 10mm out of balance. And this is the profile that I got on. I had my iPhone sitting on this. It was actually vibrating off at the end. And you can see the resonance is going through the frequencies. I didn't feel like going any higher because I was writing the pattern which something had come off. And I wasn't very high. So you can see, this is what we'd expect from a sprung. This is actually sprung with clock springs. There's a clock spring inside. So actually, and there's a valve, extremely good regulators. These you get extremely good wind from them, very little flutter. So in some respects, it's difficult to make vibrate. So you can see the frequency is about nearly 50 hertz. I came to the conclusion that the cause of the flutter was from the blowers. So I tested 7 different wind sources. So we've got this blower here, which is an old BOP blower. This one here, which is another blower manufacturer with a DC motor on there. So we've changed the speed. This one here is a 3-phase motor. This one here is another. This is the oldest blower. This is the most modern blower. This is an industrial fan, and this is a leaf blower. So you can see the spread that we've got. The only thing that changed is the blower from up here, which is to the best one there. So in fact, it's blowers 4 and 6. 4 is the best, 6 is the worst. So we go back. There's 4, the oldest, which is a Taylor of Leicester's blower. Oops. And there is the worst, which is the modern blower. Well, that doesn't mean that the one's better than the other. It just means that they are producing wind, which is exciting the resonant frequency of the reservoir. If I'd have tuned the reservoir to a different frequency, then it's possible that I would have got a different blower, which would have been better or worse than mine. And it's interesting to see, what happens here. I mean, you'd expect that from the leaf blower, but you'd expect by the time we got here, things had started to settle around. This is a comparison of the 4 sorry, the 8 blowers. So we've got the static pressure is roughly about the same. There's 6, there's 4. The number of blades, well, 6 has got a lot more blades than 4. The peripheral speed, well, there's not a lot of difference between 4 and 6. But this is the key, the actual width of the impeller. 6 is a lot wider than 4. And so I came to the conclusion that probably the impeller width is an important factor if you're going to think about designing a blower that's got or produces the least or excites the reservoir to give you the least flutter. Speed was a factor as well. 2 kinds of speed, 1500 RPM, 3000 RPM. You can see the difference here. This is for a weighted reservoir, so you've got the mass is the dominant feature. So you can see that the slow speed blower is better than the high speed blower. And here for a sprung reservoir, you can see that the frequency moved, so it's no longer about 10 hertz, it's up to about 15, 16 hertz. With a totally different waveform. And there again, well, less dominant is actually the difference in speed. And if you go back to the original measurements that we took, we can see these 2 side bands. And you actually, with a weighted reservoir, you can change the mass, change the frequency. So you can see how we got this peak here at about 10 hertz, which corresponds to the 2 side bands, 10 hertz side bands. So we're on the right track. Oops. So I wrote a script to try and simulate that. So we've got the mass of the lid and anything that's on top of it. Any spring force, well, in this instance where we're looking purely at weighted, can't really see it on. The area, so you can change these are drop-down menu. No, those are sliders. This is a drop-down menu. We can actually multiply this by 10. And the depth. And this is other stuff that's going on here about the ribs, which is more relevant to double right reservoirs. Somewhere on there is the pressure. We've got 2 pressures. One is the rib pressure and the other is the total pressure. The important thing that we're interested in organ building is pressure, because that's what supplies the pipes. So this is a typical plot for a weighted reservoir with a mass of about 100 kilograms. So James Mass took my original MATLAB script and produced this. So this afternoon, if you want to amuse yourself, you can go online and you can put some numbers in here and you can work out what you'll get from different masses, areas, depths. The key to this is damping in some respects, so I'll talk a little bit about that later. But the important thing is pressure and the resonant frequency. And here we get a Q factor. So you can see for a weighted reservoir, it's a fairly high Q factor. And when we go to a strong reservoir, it's relatively, it's a third. Still the same pressure, far higher resonant frequency. And hardly any mass. The only mass there was in the wood itself, of the reservoir. So weighted reservoirs, the mass is the dominant factor, and changing the mass changes the resonant frequency. And the higher the mass, the lower the frequency. Sprung reservoirs, changing the spring force changes the pressure, but has no effect on the resonant frequency. So once you've got the resonant frequency, then it's not going to change if you change the pressure. And these here are to do with double rise. So changing the rib angle. You saw there was an angle for the ribs. If you change that angle, it has no effect on the Q factor. And neither does it have any effect on the resonant frequency or the wing pressure. Just down the road in Manchester, the new cathedral there, they had one or two problems with the wind supply there. It's not unusual because it's always difficult to predict what's going to happen. So they effectively tune the reservoir. You can see here by changing the percentage of weight and sprung that you can actually change the effect that it has on this resonant frequency. They were able to do that by trial and error. Now, Blackpool Town, we've talked now about making good steady wing. This survives by wobbly wing, or doing exactly the opposite by using a tremulant. So in this clip, you'll hear for the start the straight organ, and then you'll hear when he puts the tremulants on. You hear the difference? It gives the organ the character it's got. So originally, when these first came out, they were in the wind system and they used to shape the organ. So they declared in 1693 that it's not got it used with full organ, and you can see why. That's just a gentle tremulant. So then you alter the amplitude by changing the weight, or you can move it further. I didn't have a lot of space here, so I had to put a big chunk of metal on the end, and changing the frequency of the motor and changing the mass will change characteristics of the tremulant. So we're doing exactly what we didn't want, what organ flutter's about. We're actually creating that organ flutter predictably. Now this is the curved ball. In America, Austin developed what they call the universal wind chest. And this here is probably 7 feet deep. So you can go through the door, through a vestibule, a little airlock, and you come out here, and you inside the chamber that's full of air. These are the pipes that on the top here. And this is the control here. So you've got a small vertical single rise reservoir, and you can't make this wind shake. It's so rock steady. So the only way they could do it is by putting a set of blades here connected to a motor. I'll play that again. I must have touched the thing twice. Well, that's the basis of the Leslie speaker. But this was done, I think, a few years earlier than Leslie speaker. And that's the only way you can get the tremulant effect. on one of these Austin Universal Winchester. The reason they design like that is for maintenance. It's so easy if you've got a problem with the action underneath here. So easy to walk through the door and you work in there. Not lay on your back underneath somewhere, like a miner. So what next? Well, I'm hoping that someone might be enticed into taking this a bit further because I'm getting to the end of it now. We talked earlier about damping, and it's so difficult to determine what the damping effect is of a reservoir. And this is a plot from a scope I made that's a reservoir that's resonant frequency 16 hertz. And it takes about a second for it to decay. Effectively, I hit that, produce this impulse response with a small valve that allowed the air out for 1/10 of a second. And that's what happened to the top. I tried several other ways to attenuate by providing these attenuating devices. This is never tested that. That's an organ builder arrangement where you've got in here effectively drinking straws, which is an anti-turbulent or straightens the airflow. These are 4 silencers I built myself, and I look at this one in particular. This is just a pepper pot one, perforated metal pipe down the middle, surrounded by mineral wool. And these are the results. These are the pots of tuning the reservoir we saw that would have probably gone on in Manchester Cathedral. This is the plot of what this thing produced here. So you can see the attenuation. And if you look at these here, this is effectively the plot that we would have got, or the plot that we got without this in. And this is what's happening on top of the reservoir with it in. So you can see it's quelled the flutter down almost completely. So there's some further work to do there. And then there's consider the dynamic behavior of when you're playing the organ. So this is a small setup that we had at the works. So unfortunately, this is someone was supposed to take on my research and it never happened, and this has disappeared now. But this was set up as a little organ connected with a MIDI system. So you could actually record and play a tune predictively and see what was happening to the wind system and listen to it to see if you could tell which system was better than another. And the last one is fan performance. We talked about quantity. So these are the curves that you get when you, this is quite a big fan. So you've got the mechanical efficiency here. And my research was based here, no flow. So it was only probably 10% efficient. And fans are designed so that you've got a maximum efficiency when you've got the maximum static or the static pressure that it's designed for here. And this is the horsepower taken from the motor. And this is the noise it produces it. So you want the minimum noise for the maximum flow. The thing about an organ builder blower is it's going from here when the organ's doing nothing to here when it's playing full organ. And if you remember the comparisons I made here, and I said that I think there's some merit in somehow trying to change the impeller width. Instead of having a one wide one, to have one that's half as, well, 2 that's the same thickness, if you understand what I mean. Thank you. That's about it.
Do you have any questions in the room at all?
Yep, one from Joe, and then I'll go to Josh. So, 65.
When you were looking at your impellers, I wondered whether you looked at the spacing between the end of the blades and the cowl that they run in at all.
Yeah. Well, you've got, there's two, the sirens, the at one extreme, the cutoff distance is quite tiny. So you get a frequency, a passing blade frequency. And I found that the cutoffs that we're talking about in organ building doors, the passing blade frequency is not really important. There's a whole loads of tests I did considering passing blade frequencies, because that's the obvious thing that you think that's where it's coming from. Sorry, it's not coming from there. Or I can see it coming from there.
Alan, so this resonant frequency you're getting for your reservoir, are you assuming that the springiness is entirely from the volume of air, or does the actual kind of like the accordion structure have some mechanical stiffness that's also having an effect?
Well, it may do. That needs to be investigated, and that's why you need some young person to take this on board and look into it. It will have to. I mean, the French organs, they have far deeper concertinaed type reservoirs. So because they're deeper, they would tend to have a lower natural frequency. And there's a lot of research needs doing between what musical effect you can get from the tremulant, because from a tremulant, you typically want a frequency of about 2 or 3 hertz for a classical organ. For a cinema organ, you're probably up in 8 or 9 hertz, and it's a case of choosing the wind system to suit what you're trying to do. So the modern cinema organs, they've got small sprung reservoirs because they have a higher resonant frequency, and the older classical organs tend to have bigger weighted reservoirs.
Thank you.
I mean, with tremulants, I think there's only really one sweet spot. They do provide you with a control to kind of adjust things, but you find that there is only, and the other thing, it depends on the frequency of the pipe. All these things come to effect. And the other thing, more importantly, is probably scaling the width of the pipe. The cinema organs work really well because they have wide scaled flutes, tibias. So part and parcel of my research was to do a survey of nearly 100 organs. We checked out which pipes were more susceptible to flutter than others. And it was the wide scale flutes that were more susceptible to flutter than the thin scale strings.
Any other questions in the room?
Curious about the Greek organ that you mentioned at the start of the presentation, and what record of that has been preserved? Is it written text or?
It's from bits and pieces of parchment, I think, with a little bit of photoshopping and of detail. If you that's generally the accepted version that I've shown you there, but there are other versions. You know, if you look at the early portative organs as well, but that was the only way that you could effectively pressurize things in those days reliably. You know, you want to, if you get an old pair of bellows for getting the fire going. It's difficult to get the pipe working on that because the pressure's changing all the time. Whereas, you know, that's the classical way of pressurizing the gas that we used to have in the old gas holders. So you actually get a steady supply of air at the right pressure. But it's got all the features of a modern organ: pipes, wind, control.
Do you still think the organ would be the king of the instruments if it wasn't in such a nice acoustic kind of space?
Well,
Because I think that would sound pretty terrible if they were outside.
oh yeah, I mean, I wrote an article for the ISO, the International Society of Organ Building, about the best up on the organ. And it's without doubt the acoustic. Bach, he had an acoustic of about 5 or 6 seconds, I think. And it makes a huge difference.
So then it's not really the king of the instruments. It's that's a bit of an, you know.
Eject that man. It is, you're right, but I mean, it's like a saxophone. You know, you've heard Trevor playing down the mine, and it sounds fantastic. Put him in the anechoic chamber, and it doesn't sound anywhere nearly as good. And the other thing is about the acoustic is that you can actually, you don't have to be as clean with your playing. If you're actually playing a very lively acoustic, you can make quite a few mistakes and they don't really come through. Whereas if you're playing in a room that's got an acoustic of about only 2 seconds, you can hear quite a few mistakes. You know, it's the drier the acoustic, it certainly amplifies them. I forget what the acoustics were in Maxwell Hall when we had the organ there. It's quite a nice building, nice room to play in. Because it made a big difference when people came in from the rain with the raincoats all wet. You know, it did actually make a difference to the acoustics.
If that's it, we're just about out of time. So I just want everyone to thank Alan again for what we should get.
Thank you.